All right, so it is now a good time to talk about password cracking. So we don't store the passwords. In 1990s, most of the web pages stored them as plain text, and their database or files they were storing it were leaked, and they, had to bankrupt at the end. So simple thing is to store their hashes. Leakage of the database then should not leak the passwords, only the hashes will leak. Hence, the hash function should be premise resistant. Okay, but even if we use hashes, what can the attacker do? I mean, if we simply if we don't use any salts or anything, if we simply take the SHA-1 or SHA-2 of the passwords and store them, what can the attacker do? Attacker can perform two attacks. Dictionary attack, since the passwords are not secret keys that are randomly generated zeros and ones, they are generated by humans. They should include some, characters that are printable, because you're creating them with your keyboard. So dictionary attack actually gathers every word from any language, combines them, add a number to the beginning or at the end or in the middle, then put a special character and so on. So you create a dictionary with these combinations, okay? Maybe gigabytes of data. Then you calculate the hash of them and check if it is in the leaked database. In the exhaustive search, you try one by one. So dictionary attack, I really like this cartoon. And actually, this should give you the satisfaction when you perform the dictionary attack and capture the password. But the idea, again, is as follows, as I just briefly mentioned. Pre-compute the hashes of common words on a dictionary, their combination with numbers, special characters, etc. Keep them sorted in a table. And here, quick sort is really fast. You can sort gigabytes of data in a very short time. Then the attacker can capture the passwords if their hash values are already in the table. So you create this dictionary before actually the database leaks. Okay? You create your dictionary, then the database leaks. So you check if any password is there. And by the way, this attack still works. People still keep their passwords in a hashed way. So the countermeasure is using salts. Instead of hash of a password, when somebody creates an account, at that time randomly generate a salt, concatenate it to the password of the user, then calculate the hash of it, okay? So attacker has to generate tables now for every salt, which is not practical, right? And generally salts are like 32 bits, but you can use something longer. So in the database now, instead of storing username, hash of the password, now you store username, salt, and the hash of the password concatenated with salt. So salts also leak when the database leaks, okay? Otherwise, you cannot, use it in practice. Now, assume that we use salts. So dictionary attack is not practical. So what you can do? You can perform exhaustive search or brute force attack. So when a hash and a salt value is obtained, calculate hash of every possible short password concatenated with the salt, and check if the hashes are identical to the one in the database. So, how hard is the attack? Let's look at 8-character password search space, because still on the internet, people say that 8-character passwords are secure. So let's see why it is not. Okay. So English alphabet has 26 letters. With the capital letters, we get 52. If we add numbers, we get 62 possibilities, but there are like 94, sometimes 95 printable characters in ASCII, right? Depending on maybe on your keyboard, let's say. So if you use only small letters in the English alphabet, every character can take 26 different values, and we are talking about 8-character passwords, so you can actually generate 26 to the 8 different passwords, right? Which is, as a power of 2, it is 2 to the 37.60. So it looks like a large amount, but if you have the fastest GPUs, maybe you can even calculate this many passwords in a few seconds. Okay. So this is why when you create a password, they also say to you that also use a capital letter, right? So now your password space increases. Then they also say you to use a number. it also increased, but not that much. But they also ask you to use a special character. So it is now this. But if I can perform 2 to the 32 or more hashes in a second on a GPU, and actually with modern GPUs, you can even do 35, 2 to the 35, then you need to perform this search for 2 to the 17 seconds, right? So it is just 1 or 2 months. On a single GPU, I can try all of these passwords in a month. So as you can see, it is not secure. Okay. And actually, you can do something clever. We can search the space in a clever way. Users select easy to remember short passwords. They almost never use more than 2 special characters. Actually, I mean, I don't want to give any advice to attackers, but what everybody do is use a single capital letter, use a word in short, small letters, put a number, then a special character, right? So the space is now a little bit short compared to all of the possibilities. All right, so how can I solve this problem? If 8-character passwords are not secure in this way, you can suggest users to use longer passwords. But using 12 or longer character passwords is not practical. People will start forgetting their passwords. So I should come up with a way where I can make 8-character passwords secure. Okay. So what you can do is as follows. Instead of using the hash value of a password, repeatedly use the hash output as the hash input. So this is the slowdown of the hash computation. For instance, if you repeat this hashing operation 8,000 times, this makes the attacker's jobs 8,000 times harder. I chose 8,192 because it's the power of 2. And actually in all of this software, you choose actually the power of 2 to be your repetition count. A few years ago, this was the default in Linux, but I think it shouldn't be nowadays. So let's move on to password-based key derivation and see how passwords can also be used to provide secret keys and how we can capture those secret keys by capturing these passwords. So password-based key derivation function 2. It looks like as if I randomly press a few buttons, but it is a abbreviation. This is a key derivation function that is part of RSA Laboratories, public key cryptography standards, also published as Internet Engineering Task Force RFC 2898. So this function produces desired key, okay? As the input, it takes pseudo-random function, password, salt. C is the number of times this pseudo-random function going to be used, and dklen is the length of the secret key you prefer. So, for instance, if you want to use AES with 256 key bits, this would be 256. But sometimes you need longer keys, like for instance in RSA, you might ask this to be 3072 bits, right? So this algorithm actually, from your password, it actually generates a secret key for you. So yeah, these are the abbreviations. So it works like this. Each HLAN bit block TI of derived key decay is computed as follows. So you calculate TIs and then concatenate them. And TI is calculated as follows. For your function, you provide password, salt, number of calculation times, and I. Okay, where F is the XOR of C iterations of the chained pseudo-random functions. Again, here actually you are XORing all of the UIs. So initially U1 is calculated like this: password, salt, concatenated with the number I represented as 32-bit integers with big N notation. Okay, you calculate U1, then U2, and so on and so forth. Then you XOR all of them. So let's see practical use cases. So VPA2 uses this password-based key derivation function. So at home, when you use your Wi-Fi modem, actually you choose a passphrase, right? So this is your password in this algorithm. Let me go back. Then this actually needs a salt. So you might ask, what is the salt in my Wi-Fi modem? Actually, this is your SSID. So salt is also chosen by you. The output is 256-bit key because it is going to use AES 256. And C is chosen as 4096. So SHA-1 in HMAC mode will be calculated 4,000 times to provide a secret key for to generate your AES key. So this is why if you choose a bad passphrase, somebody listening to your Wi-Fi communication can actually brute force your secret key by using this algorithm, okay? So this is why you shouldn't choose a easy to remember passphrases or very short passphrase, okay? Because 4,000 times is not that large. Think about as the power of 2. So this is 2 to the 12, right? So if we go back, I said that I can try, I mean, the password space is this. But if you use the VPA's formula I use, it doesn't only calculate one hash, but it calculated 4,096 times. So if you increase all of these powers with 12, that is the number of operations you need to capture 8-character Wi-Fi passwords. So even in this scenario, it becomes 64. 2 to the 64 is within our reach if you have many GPUs and so on. Okay, think about the collision attack of Mark Stevens et al. They performed in their initial attack, they performed 2 to the 57 SHA-1 calculations just using 64 GPUs. Use thousands of GPUs, and you can actually capture every 8-character passphrase, right? So this is why at home, this shows you that since this number is small, you should choose a passphrase larger than maybe 9 or 10 characters. Another use case is WinRAR. But WinRAR use something more clever. Instead of 4,000, they choose 2 to the 15, just 32,000. So, but this time it doesn't use SHA-1, it uses SHA-256. Okay. So in WinRAR, I mean, normally it is a compression software, but if you want also confidentiality, you say also encryption, and there they ask you to choose a password. So if you choose 8-character password, it wouldn't be secure for VPA2, but it will be secure for WinRAR because trying every 8-character, if it is randomly generated, would be very hard. But this also means that if you choose your WinRAR password like 10 characters, and if you forget it, nobody will be able to get it, right? But this also gives a company strategy, right? You can create a company where you buy a lot of GPUs and your service will be to recover forgotten passwords of people. You can make good profit from it. Yes, our analysis shows that WinRAR passwords longer than 8 characters are secure. Years ago, we did a work on, optimized implementation of SHA-256 using a GTX 970 GPU. So length also depends on the characters you use. I mean, if you only use numbers, but if it is 12 characters, then on a GPU it takes 20 years to try all of the 13 characters. But if you have thousands of GPUs, this is within reach. So don't think that long is enough. If you only use numbers, then we can break it. So if you use numbers and characters, but if it is length 6, we can break it easily. If your length is now 7, we can still break it. It is within our reach. And 8 characters takes years. But again, this is within our reach because we can, for instance, if we have 439 GPUs, then it will take 1 year, right? And don't forget that this is an old study. This GPU is outdated right now. I mean, if you have 4,090 GPU of NVIDIA, you have to, divide all of the numbers by maybe 10 or 20, depending on the implementation. So this is why every web page asks you to use a special character. So if you look at the printable characters, 6 length is easy. 7 characters, again easy if you have a few hundred GPUs. 8 characters will take 13,000 years. But again, if you have 13,000 GPUs or if gamers get together on the internet, they can perform this operation for a few days and capture the 8-character password, because there are thousands of, maybe millions of gamers with many good GPUs, right? So for this reason, you have to exceed to 9 characters here. 8 is not enough. So here actually comes the question. This is, hiding the password with using hash functions and so on looks like ad hoc methods, right? There are no standards here. So for this reason, there was a competition, because people said that password hashing is everywhere, but there wasn't established standard to fulfill the needs of modern applications and to best protect against attackers, right? So cryptographer John Philip Almoson in fall 2012 initialized a competition, password hashing competition, PHC, and the web page is here. It received 24 submissions, and 9 finalists are announced in December 2014. In July 2015, Argon 2 was announced as the winner. Okay, I don't think that many people heard this, but there's an algorithm which actually designed so that it will be still resistant for ASICs and so on. So he tried to design it so that the hashing power shouldn't be that much for serious attackers. 4 other finalists are received special recognition, and they are here: Catena, Lyra 2, Magpie, and Yescript. For instance, Lyra 2 is used in many mining algorithm of alternative cryptocurrencies. Okay, so instead of using SHA-256, maybe looking at the winner of this competition and using it for storing passwords might be a good idea.